Hi, this is Tawhidul Islam. I have been working on a project to optimize call center operation, and today I will be presenting the progress of my project. The objective of the project is to improve call center performance by minimizing waiting time. In this study, we focus on several key assumptions, including calls arriving following Poisson cerebral process in a two-server system. We will discuss the assumptions later on. In this study, we will try to address a few questions, which includes: do call arrive randomly and independently? How efficiently the servers being utilized? And if we can improve the waiting times. Before jumping into the details, let's look at some background of call centers. The first known call center in the history used Private Automated Business Center, also known as PABX, back in 1960s. But later in the early 70s, call center started using automatic call distributor to distribute incoming calls to the best available agent. This automatic call distributor used to use first in first out queuing method, which means the customer arriving last need to wait till the customer before him is served. This significantly increases the waiting time, and to improve this problem, skill-based routing was introduced to assign calls to the agent, not only based on the availability, but also based on their skills. This dynamic process significantly reduces the number of customers in the queue and improve the call center performance. In our project, we will also be using the skill-based routing. Now let's come to the mathematical modeling. In this study, we will build a mathematical model using Markov decision process to find the optimal policy so that we can reduce the waiting cost. To implement this model, we assume a system with two servers where we have two types of call, and server 1 handles both types of call and server 2 handles only type 2 calls. We also assume the calls are arriving following Poisson cerebral process and distributed exponentially. We also assume that the system is finite, which means we will not receive any new calls after hours. To implement Markov decision process, we assume a state space, which is a tuple of customers in queues and the status of the agents. There will be an action space, which is the transition of type 1 but type 2 calls to server 1 or server 2. Then we will calculate the transition probability, which is the probability that we are in current state given that previous state, and this is calculated using the probability mass function. Next, we find a reward function, which is mm, proportional to the total number of customers waiting in the queue. And from this, we calculate the expected reward using the Bellman equation. And as stated, that the goal is to always minimize this expected reward, which is our optimal policy. Now we jump into the simulation. If we can see the optimal policy heat map. The actions are denoted by numbers. At the very beginning, we have no actions, so we got uh, mm, the heat map denoted by 0 here. Then we have type 1 calls being served denoted by 1 and type 2 calls served denoted by 2. And another actions of serving both calls simultaneously is denoted by 3, which happens when the server is overloaded. The goal is to reduce the waiting cost, which also means lowest possible customers in queues. Here we can see the length of the queues, both Q1 and Q2, and we have less than one customers in queues. In our simulation, we set the maximum number of customers in the queues is up to 5, but we see from the simulation we have even less than one customer in queues, which is very good uh, for a call center. And we also have less than -2 immediate average reward, which is also seems good for the call center. Now we got our real-time call center data with 5,000 call entries. This is a slightly modified data with two agents where we saw 81% of answered calls. We did some pre-processing, including handling missing data, converting time columns, or converting yes no to 0 1, etc. Here are some visualization of the data where we can see we have two agents named Sarah and Tom. Most of the calls uh, are being handled by Sarah, but the percentage of calls answered by both of the agents are almost equal. Also, the percentage of resolved calls and the average speed of answers of the two agents are almost. Now we need to validate our assumptions. First of all, let's see if we have two servers having one serving both types of calls and other only one type of calls. Here we assume that the contract and payment related calls are type of calls and the admin support, streaming and technical support are type 2 calls. So from the plot, we can see that Sarah is handling both type of calls while Tom is handling only type 2 calls. Therefore, we can say that the server assumption is valid. Now let's validate if we have a finite horizon. From the plot, we can see that the calls drop near zero at the last hour and no further calls are coming, which suggests this is a finite system. Finally, we check if the data validates Poisson's arrival process. From the inter-arrival time distribution, we can see some unexpected negative values that suggest ordering issues or incorrect timestamp. We also see a sharp peak near zero. This suggests highly clustered arrival rather than following a Poisson-like random process. And there is a highly skewed distribution, and the left tail has negative values, which is not correct. So to fix this, we sorted the date time and removed the negative inter-arrival times, and this is what we got. So we have the right skewed distribution, which is exponential with a long tail. This is expected for Poisson's arrival. However, we still got the sharp peak uh, near zero, which suggests drastic calls arrival like real world call center. This is suggesting that this is not standard Poisson's distribution. So to be more sure, we looked at the arrival rate change. Uh, so here we can see the in the middle we have a good fit, but at the tails we have some deviations. So we did more tests to be confirmed if we have the poison arrival or not. So these are couple of more tests. The first one is the mean variance test, which is according to the Poisson's property, the mean should be equal to the variance, and what we got is the mean of arrival and the variance of arrival is almost equal, which suggests the Poisson's assumptions is likely to be valid. But according to the case test, the extremely small p-value uh, reject the null hypothesis, which means that the data does not follow the Poisson distribution. Therefore, we can conclude that the data fails to satisfy our important assumption of Poisson's arrival. So, we are now unable to use the Markov decisions process as our mathematical model because for the Markov process, we use the data arriving to our system to be following Poisson's arrival. But here, the real world data does not follow the Poisson's arrival. So we are now exploring new models, including a reinforcement learning algorithms such as proximal Polysium optimization. So this is all for today. We will be keep working on improvement. Thank you for your patience. Have a good day.